As instrument technicians, you've probably learned that the primary function of any process control system is to maintain a plant process at or around a predetermined value called set point. For example, control systems are used to maintain process variables such as level, temperature, flow rate, or pressure at or within desired values. To achieve control, a control system performs certain basic functions. It measures a process variable and compares the measured value to set point. If these two values are not equal, the control system responds to bring the measured value back to set point by manipulating a process variable. These functions can be illustrated on a simplified logic diagram. A circle represents an instrument that performs either a measuring or readout function. This one performs a measuring function. The measuring function for pneumatic control systems is often performed by a transmitter that measures the value of a process variable and produces an output signal that represents this value. A process variable that is measured is sometimes called a monitored variable. The output signal from the transmitter is sent to an automatic signal processing instrument, which is represented by this rectangle. In pneumatic control systems, automatic signal processing is usually accomplished by a controller. A controller compares the signal from the transmitter to set point. If necessary, the controller produces a corrective output signal. The output from the controller is sent to a final control element, which is represented by this figure, called a trapezoid. The final control element, such as a valve, manipulates a process variable. A process variable that's manipulated is often called a manipulated variable. By manipulating the variable, the control system maintains the process variable at set point. A process variable that is maintained at a predetermined value is also called a controlled variable. The diagram we just saw is representative of a single-element control system. A single-element control system usually monitors one variable and manipulates one variable to maintain the controlled variable at set point. However, many of the control systems that you'll have to maintain, troubleshoot, and repair aren't that simple. In multi-element control systems, for instance, more than one process variable may be monitored and more than one process variable may be manipulated to keep a controlled variable at or near a desired value. This means that a multi-element control system can have more than one measuring element, more than one controlling element, or more than one final control element. Our objective in this program is to learn how multi-element pneumatic control systems work to maintain a process variable at or close to a desired value. To approach this subject in a way that will be useful to you as technicians, we'll examine several multi-element pneumatic control systems that are often used in the plant. We'll take a look at the overall design and function of a process, and we'll see how the individual instruments and components in the system work together to keep the process variable at set point. Of course, control systems vary in design and operation, so the examples we'll use may not be exactly like the corresponding systems you'll have to work on. However, the general principles of multi-element process control that we'll discuss can be applied to systems you'll encounter in your plant. In your training, you've probably learned about single-element control systems. So a good way to introduce multi-element systems is to see how two single-element systems working together keep a single controlled variable at set point. Let's take a look at an example of how this is done. Here we see a simplified illustration of a heat exchange process that's used to convert water into steam for use in the plant. This particular system is designed to keep the steam leaving the heat exchanger at a specific pressure. The heat exchanger consists of a shell, and in the lower section of the shell are tubes. In general terms, the system works like this. Water enters the shell through this line to maintain the level in the shell at a predetermined value. At the same time, steam flows through this line and into the tubes. As steam circulates through the tubes, it heats the water, turning the water into steam that flows out of the heat exchanger through this line. As it heats the water, the steam in the tubes condenses and is drained off through this line. In this example, the controlled variable is the pressure of the steam at the output of the heat exchanger. The steam pressure is maintained by two variables: the steam flow through the tubes and the level of water in the shell. If there is either too much or too little steam flow through the tubes, the water in the shell won't be turned into steam at the proper rate, and the steam pressure leaving the exchanger won't be maintained at the desired value. By the same token, if the water in the shell is not at the proper level, the steam leaving the heat exchanger will not be properly maintained. What we need then is a control system that can maintain the proper flow of steam through the tubes and maintain the proper level of water in the shell. So let's add the necessary instruments and see how they automatically manipulate steam flow and water level to maintain the proper steam pressure out of the heat exchanger. In this example, the value of the steam pressure at the output of the heat exchanger is monitored, and this value is used to control the flow rate of the steam entering the tubes. The steam pressure at the output of the heat exchanger is conveyed through this line to a pressure controller. This controller combines the measuring and controlling functions in one instrument. To find out more about this controller, let's take a look at a simplified logic diagram for this system. We'll be referring to logic diagrams throughout the program to help explain the functions of the control instruments. These letters in the circle, PT, tell us that the measuring part of the instrument is a pressure transmitter. The symbols in the rectangle tell us the specific control action that this controller takes if its input signal changes or deviates from set point. These symbols tell us that the controlling part of the instrument is a proportional plus integral, or PI controller. As you may recall, a proportional controller produces a change in output that is proportional to any change in input. Integral or reset repeats this proportional output as long as the process variable is away from set point. The purpose of integral control is to eliminate offset by ensuring that the control system takes the necessary action to return the process variable to set point. By looking at the logic diagram and learning that the controller is P plus I, we can conclude that the process variable must be maintained at set point and that it can have no offset. Returning to our illustration of the system, we see that the output from the controller goes to the final control element. The final control element in this system is a valve that's operated by an actuator with a positioner. When the output from the controller changes, the actuator moves a valve plug inside the valve to a new position. To learn more about the final control element, let's look at the logic diagram again. These symbols indicate that the final control element is a non-linear device. To understand what is meant by non-linear, let's take a look at an illustration of a gate valve. The valve to regulate steam flow in our example is not a gate valve, but a gate valve is useful to explain what non-linear means. We can see in this side view that the valve stem is connected to a valve disc. When the valve stem moves, the valve disc moves with it to manipulate flow through the pipe. The relationship between stem travel and disc travel is linear. When the stem moves 50% of its total travel, the disc also moves 50% of its total travel. However, the relationship between stem and disc travel and the percent of flow through the pipe is nonlinear. When the stem and disc move to 50% of their total travel, there will be more than half of the total flow through the pipe. This is indicated by the shaded area, which shows that more than 50% of the pipe is open. The reason for this is the shape of the pipe and the shape of the disc. For this final control element, non-linear means that a specific percentage of valve disc movement will not necessarily result in the same percentage of change in flow. The final control element acts to manipulate steam flow. The positioner and actuator respond to the signal from the controller and position the valve plug to regulate the steam flow through the tubes. Now that we've seen how the steam flow's control system is set up, let's take a look at the control system that's designed to maintain the level of water in the shell. As we said, the water level must also be controlled to maintain steam pressure out of the heat exchanger. In this system, the water level is sensed by a displacer that's connected to the level controller. Like the pressure controller we saw, this level controller also combines the measuring and controlling functions in one instrument. Let's check the logic diagram to learn more about this controller. The letters LT tell us that the measuring part of the instrument is a level transmitter. We can see by these symbols that the controlling element is a proportional plus integral controller. This ensures that if the level moves away from set point, the output from the controller continues to adjust the final control element until the level is returned to set point. The signal from the controller goes through this line to the final control element. The final control element is also a valve that's operated by an actuator with a positioner, similar to the steam valve we saw earlier. If we look at the logic diagram again, we can see that this final control element is also non-linear. The positioner and actuator respond to the signal from the controller to regulate water flow into the shell and maintain the water level. These two control systems, the steam flow system and the level control system, work together to keep the output steam pressure of the heat exchanger at set point. There are two monitored variables, water level and steam pressure. If the value of either monitored variable changes, its system will respond by manipulating either steam flow or water flow to bring the monitored variable back to set point. In the example we've looked at in this part of the program, two separate control systems were used to help maintain a single controlled variable at set point. The steam flow system and the level control system are both needed to keep the steam pressure out of the heat exchanger at the desired value. At this point, take some time to review this information by reading over the first part of your text and answering the questions. Also, be sure to clear up with your instructor any problems you might have with the material. In the last part, we saw how two single-element control systems can work together to maintain a controlled variable at set point. To accomplish this, each of the control systems monitored a different process variable. In this part, we'll see how one control system monitors more than one variable to maintain a controlled variable at set point. One type of multi-element control system that does this is a ratio control system. As the name implies, a ratio control system maintains a predetermined ratio between two or more process variables. In general terms, a simple ratio system monitors two variables and manipulates one of the two to maintain the desired ratio. Let's examine this basic idea further by looking at a simplified logic diagram of a ratio control system. In this system are two measuring elements, a controlling element and a final control element. Each of the measuring elements monitors a different process variable, and each provides a separate input signal to the controlling element. These signals represent the values of the monitored variables. In a ratio control system, the controller uses one of the input signals to establish set point. The ratio controller compares the other input signal against set point. If there's a difference between this input signal and set point, the controller produces a corrective output signal that represents this difference. The corrective output from the controller is sent to the final control element. Since there's only one final control element in this simple ratio system, the system can manipulate only one of the two monitored variables. More specifically, the final control element acts to increase or decrease the value of the manipulated variable. As the value of the manipulated variable changes, the measuring element senses the resulting change in the monitored variable and produces a change in its output signal. This signal is fed back into the controller. When the input signal equals set point, the output from the controller holds the final control element in the new position, and the system is balanced at the proper ratio. In the system we just saw, two variables were monitored, but only one of the two was manipulated. The variable that's not manipulated in a ratio control system is called the independent variable. Its value depends only on the demand of the plant and is independent of any action taken by the control system. The variable that is manipulated by the final control element is called the dependent variable because its value depends on the control action taken by the system. If we apply the general concepts we've investigated to a specific plant process, we can get a clearer picture of how ratio control works. We'll look at a system that removes suspended particles from wastewater by mixing a chemical with the wastewater. It's called a water clarification system. First, we'll take a look at the basic function of a typical water clarification process. Then we'll examine a ratio control system designed to maintain the proper amount of chemical in the wastewater. In this simplified illustration are some of the major components of a water clarification process. This particular process consists of a mixing tank and a settling tank. Wastewater from the plant flows through this pipe and into the mixing tank. A chemical solution flows through this pipe and into the mixing tank, where the wastewater and chemical solution are mixed at a specific ratio. The mixture is then transferred to this settling tank. The chemicals in the mixture cause suspended particles to settle to the bottom of the tank. The clear water on the top is drained off through this pipe and, after going through further cleaning processes, can be reused in the plant or discharged to the environment. An essential requirement of this type of water clarifying process is that there must be a specific ratio of chemical solution to wastewater. If not enough chemical solution is used, not enough of the suspended particles will settle out. On the other hand, using too much of the chemical solution is wasteful. Therefore, in this example, the controlled variable is the ratio of chemical solution to wastewater. To maintain the proper ratio of chemicals to wastewater, a ratio control system is used. So let's add a ratio control system to our water clarification process and see how it works. The control system for this example includes a flow transmitter to measure the flow of wastewater and a flow transmitter to measure the flow of chemical solution. Each of these transmitters provides an input to the ratio controller. The ratio controller compares the two input signals and computes the ratio between them. If the two input signals do not compare at a predetermined ratio, the ratio controller produces a corrective output signal which goes to a final control element. The final control element for this system is a control valve in the chemical solution line. This valve manipulates the flow of chemical solution to maintain the desired ratio between chemical solution and wastewater. To examine the control function of these instruments further, let's refer to a simplified logic diagram for this system. The letters in these circles tell us that the measuring elements in this system are flow transmitters. This represents the controlling element. The ratio controller is different from the controllers we saw earlier, and some of the symbols are also different. This symbol indicates that the controller performs a multiplying or ratio function. In other words, one of the monitored variables is maintained at a predetermined multiple or ratio to the other monitored variable. As before, these two symbols tell us that this is a proportional plus integral controller. Proportional plus integral control is required to ensure that the ratio between wastewater and chemical solution is maintained at set point. The signal that represents the value of one monitored variable establishes set point for the other monitored variable. The controller compares the signal that represents the other variable to set point and, if necessary, produces a corrective output signal. The output from the controller operates the final control element. This symbol indicates that the final control element is nonlinear. In our example, wastewater flow is not constant. It varies with the demand for water in the plant processes. Since wastewater flow rate is not regulated by the control system, it's the independent variable. In contrast, the chemical solution flow is directly dependent on the action of the control system. Its value is manipulated by the final control element. Therefore, the chemical solution flow rate is the dependent variable. Up to this point, we've seen the instruments used in this system, and we've examined their control functions. Now let's see how this control system maintains the ratio between chemical solution flow rate and wastewater flow rate. This flow transmitter measures the flow rate of the wastewater and produces a signal that is sent to the ratio controller. The ratio controller uses this signal to establish set point for the chemical solution flow rate. The chemical solution flow rate is measured by this flow transmitter, which produces a signal that is sent to the ratio controller and compared to set point. The controller computes any difference between the signals and produces a corrective output signal that operates the final control element. The final control element responds to changes in the output signal from the controller and repositions itself to change the flow rate of chemical solution. The transmitter measures any change in the flow rate of the chemical solution and changes its output signal accordingly. The output from the transmitter is fed back to the ratio controller, where it is again compared to set point. If there is still a difference between the signal that represents chemical flow rate and set point, the controller continues to send a corrective signal to the final control element. The final control element manipulates the chemical solution flow rate until the signal from the chemical flow transmitter and set point are balanced. When this occurs, the system is in balance and the proper ratio of chemical solution to wastewater is achieved. By now, you should have a basic understanding of how ratio control systems are used in water clarification processes. In ratio control systems, the key point is that the controller maintains a predetermined ratio of one variable, such as chemical solution, to another variable, such as wastewater. You can explore ratio control further by discussing with your instructor other ratio control systems you'll encounter in your work. After you've had a chance to read over the material in your text and answer the questions, we'll move on. In the last part of this lesson, we looked at a special type of multi-element system whose function was to maintain the proper ratio between two process variables. For the remainder of the program, we'll be looking at multi-element control systems designed to automatically control the operation of a boiler. As you know, a boiler system is a common industrial process for turning water into steam that's used elsewhere in the plant. To produce steam, a boiler needs two essential elements: heat and water. Let's expand on this by looking at a simplified illustration of a typical boiler. To produce heat, fuel is supplied to the boiler through this line, and air is supplied through this line, or duct. The fuel and air are mixed and burned in the boiler furnace. The process of burning the fuel and air mixture is known as combustion. Water is supplied through this line to maintain the proper level in the boiler drum. As the water in the drum's heated, it turns into steam and flows out of the boiler through this line. The flow of steam out of the boiler must be able to satisfy the demand for steam in the plant. As the demand for steam changes, the amount of fuel and air needed in the furnace and the amount of water needed in the drum also change. In the system we're using, it's possible to monitor the steam flow out of the boiler to determine plant demand and use this demand to maintain the proper amount of heat in the boiler furnace and the proper water level in the boiler drum. In this part of the program, we'll see how steam flow is monitored and used to maintain the proper amount of heat in the furnace. For this process, a multi-element control system monitors steam flow and maintains the proper amount of heat by manipulating the fuel and airflow into the furnace. Manipulating the fuel and airflow into the furnace is called combustion control. This particular combustion system uses a special type of control system called a cascade control system. In simple terms, a cascade control system is a system in which the output signal of one controller establishes the set point in a second controller. The output signal from the second controller operates a final control element. To understand what we mean, let's look at a logic diagram that represents a simple cascade control system. This logic diagram is similar to the logic diagram for the ratio control system that we looked at earlier, but there is one important difference. Although this controller receives two inputs, just as the ratio controller did, one of these inputs comes from another controller. And this is the major difference between a ratio and a cascade arrangement. In most cases, when a controller receives an input from another controller, the system is cascade. In this particular arrangement, this controller receives an input from a measuring device. The controller compares that input to an established set point and produces an output signal that represents the difference between its input signal and set point. The output from this controller is sent to this controller. This input is the set point in this controller. This controller also receives an input from a measuring element, which it compares to its set point. If there is a difference between the input signal and set point, the controller's output will reflect that difference. A change in either of its inputs will cause a change in its output. The change in output is sent to the final control element to return the process variable to set point. The advantage of a cascade control system is that the control system will respond to a change in either of the monitored variables to maintain the process variable at set point. To apply these general principles of cascade control to the boiler system we've introduced, let's refer once again to the illustration of the boiler. Here's the boiler with the instruments that make up the cascade control system. In this cascade system, the rate of steam flow is used to maintain the proper rate of fuel flow and airflow in the furnace. This transmitter measures the rate of steam flow from the boiler, produces a signal that represents that value, and sends it to this controller. For the boiler used in our example, this controller is called the master controller because its output signal is the set point for both fuel flow and airflow. The master controller compares the signal from the transmitter to its set point and produces a change in output signal that is proportional to the change in input. The output signal from the controller goes to a hand auto transfer station. As you know, a hand auto transfer station allows an operator to switch the control system from automatic to manual. This permits him to control the process manually if it is not operating properly in automatic. When the transfer station is in automatic, the signal from the master controller passes through the transfer station and is the output of the transfer station. For the remainder of this program, we'll assume the hand auto stations are in automatic. The output signal from the transfer station is sent to this controller, which is the fuel flow controller, and this controller, which is the airflow controller. Since this signal is the set point in these two controllers, this is a cascade control system. To find out more about these instruments, let's see what this part of the control system looks like on a logic diagram. The steam flow transmitter is represented by this circle on the right. The output from the transmitter goes to the master controller. This symbol tells us that this is a proportional-only controller. The reason for having a proportional-only controller is that steam flow is not being controlled, but changes to meet plant demand. The only requirement for this controller is that it must produce a change in output signal that is proportional to the change in input. The output signal from the master controller goes to the hand auto transfer station, which is represented by this diamond. The T tells us that it is a manual transfer station. With the hand auto switch in the auto position, the signal from the master controller will pass through the transfer station and go to these two controllers. the fuel flow controller, and the airflow controller. This signal, which is produced by the master controller, is the set point for both the fuel flow and the airflow controllers. We've seen that the output from the master controller is the set point for the fuel and airflow controllers. Now let's see how the fuel flow and airflow systems work. We'll start with the fuel flow system and see how it manipulates fuel flow into the furnace. The part of the system that regulates fuel flow consists of a flow transmitter, a controller, a hand auto transfer station, and a valve with an actuator and positioner. The master controller establishes set point for the fuel flow controller. The transmitter produces a signal that represents the value of fuel flow. This signal is sent to the fuel flow controller. The fuel flow controller compares this signal to set point and computes any difference. It produces a corrective output signal that represents that difference and sends it to this hand auto transfer station. In automatic operation, the signal from the fuel flow controller passes through the transfer station and is sent to the final control element. The final control element positions a valve in the fuel line to manipulate flow to the furnace. To find out more about the control instruments that regulate fuel flow, let's return to our logic diagram. This part of the diagram represents the fuel flow control system. This represents the flow transmitter, and this represents the fuel flow controller. There are two input signals to this controller, one from the master controller and one from the flow transmitter. As you can see, this is a PI controller. A PI controller is used in the fuel flow control system because the amount of fuel entering the furnace is critical, and fuel flow must be maintained at set point. As we've seen, a PI controller repeats its output signal until the process variable returns to set point. This represents a hand auto transfer station in the fuel flow control system. Like the other one, it's also a manual transfer station. And here is the final control element, which is non-linear. The fuel flow control system is similar to a single element control system, but with one major difference. In a single element system, set point is manually set at a hand auto transfer station or in the controller itself. In this Cascade Control system, set point is the output of the master controller. Now that we know how fuel flow is regulated, let's go back to our illustration and identify the instruments that control airflow. The system that manipulates airflow is made up of a flow transmitter, a controller, a hand auto transfer station, and a final control element, which in this system is an actuator that operates louvers in an air duct. The master controller establishes set point for the airflow controller. This transmitter sends a signal that represents the value of the airflow to the airflow controller. The airflow controller compares the signal to the set point. If there is a difference between the input signal and set point, the airflow controller sends a corrective signal through this hand auto transfer station to the actuator, which positions louvers in the air duct. The actuator repositions the louvers as needed to allow either more or less airflow into the furnace. Let's go back to the logic diagram again to examine the airflow system in more detail. This part of the diagram represents the airflow control system. You can see that the airflow system is very much like the fuel flow system. The airflow instruments have the same features as the fuel flow instruments. The output signal from the master controller is set point for the airflow controller. The transmitter produces a signal that represents airflow, which goes through this line to the airflow controller. This controller is a PI controller. It's essential to have the right amount of air in the furnace to ensure complete combustion. And a PI controller ensures that airflow is maintained at set point. The output from the airflow controller goes through this hand auto station and on to the final control element. So far, we've seen that a cascade control system manipulates fuel and airflow in response to steam flow. Now let's see how a change in steam flow affects fuel and airflow. To meet a change in demand for steam, both the fuel supply and air supply must be changed. Let's see how this works. When the demand for steam changes, steam flow changes. The steam flow transmitter senses the change, measures it, and sends a representative signal to the master controller. The master controller compares the input signal to set point, computes the difference, and produces a corrective output signal that's proportional to its input change. The corrective output signal establishes a new set point for both the fuel flow controller and the airflow controller. The fuel flow controller compares the signal from the fuel flow transmitter to the new set point. To change the fuel flow rate to the new set point, the fuel flow controller applies proportional plus integral action to the final control element. This causes the fuel valve position to change, which changes the flow. The fuel flow transmitter senses the change in fuel flow and sends a representative signal of this new flow rate back to the fuel flow controller. When the signal from the transmitter balances the new set point, the fuel flow rate will have changed the desired amount, and the system will be back in balance. At the same time that the fuel flow is being changed, the airflow is also being changed, and by similar control action. The master controller changes the set point of the airflow controller. The controller then compares the signal from the airflow transmitter to the new set point and applies proportional plus integral action to the final control element. This output repositions the louvers on the forced draft fan, which changes the amount of airflow into the furnace. The airflow transmitter senses the change in airflow and transmits a signal representing this flow back to the airflow controller. When the signal from the transmitter balances the new set point, the system is again in balance. When both the fuel flow and airflow systems are back in balance, the heat in the furnace is changed in proportion to the change in demand for steam from the boiler. We've now seen how one controller can provide set point for other controllers in a cascade control system. We've learned how a specific application of this principle is used to regulate fuel flow and airflow into a boiler furnace, and why this is vital for efficient and safe boiler operation. However, there are some requirements of combustion control that cascade systems by themselves can't satisfy. When we return, we'll see what these requirements are, and we'll take a look at the type of control that is necessary to take care of them. For now, study the material on cascade control in your text and ask your instructor for help if you need it. In our examination of a boiler process, we've seen how a control system maintains the proper heat in a boiler furnace by regulating the fuel and air supply. For safe and efficient combustion, it's important to burn all of the fuel entering the furnace. If there's not enough combustion air in the furnace, all of the fuel may not be burned. Unburned fuel could collect in the furnace and cause an explosion. Therefore, when demand for steam from the boiler increases, the airflow must increase before fuel flow. And when demand for steam decreases, fuel flow must decrease before airflow. The manipulation of fuel and air has to occur in this order to ensure that there is always enough air in the furnace for complete combustion. The problem with the system we've looked at in this last segment is that when demand for steam changes, fuel and airflow are adjusted at the same time. To make sure that fuel flow and airflow are adjusted in the proper sequence, our existing fuel and air control systems have to be modified. This modification is the addition of a feature called Auctioneering Control. Briefly, Auctioneering Control allows a control system to respond to one of two or more input signals. To see how this is done, let's go to a logic diagram of a simplified auctioneering control system. In this system, there are two measuring elements, a controlling element and a final controlling element. Each of the measuring elements monitors a process variable, and each provides a signal that represents the value of the monitored variable to the controlling element. In auctioneering control, the controlling element responds to only one of these signals. For example, the controlling element may respond to the higher or lower of the two signals. This symbol tells us that the controlling element responds to the higher of the two monitored variables. The controller compares the higher signal to set point and, if necessary, produces a corrective output signal. This symbol tells us that the controlling element responds to the lower of the two monitored variables. The controller compares the lower signal to set point and produces a corrective output signal if necessary. The output from the controlling element is sent to a final control element that takes the appropriate control action. Now that we have some background on auctioneering control, let's relate these concepts to the combustion control system. We'll add the feature of auctioneering control to the existing control system and see how it works. For this system, auctioneering control is provided by the addition of these two relays. The addition of two relays is sufficient because there's already a controller for the fuel flow system and one for the airflow system, so additional controllers are not necessary. As you recall, in the simplified auctioneering system, the controlling element selected one of two inputs, compared it to set point, and produced the appropriate output. Unlike a controller, the relays in this system do not have a set point. They select one of the signals, allow it to pass through without being processed, and at the same time, they block the other signal. This relay receives two signals. One signal comes from the master controller through this hand auto transfer station. The other signal comes from the fuel flow transmitter. There is one output signal from the relay. It's sent to the airflow controller. This relay also receives two signals. One signal comes from the master controller through this hand auto transfer station. The other signal comes from the airflow transmitter. There is also one output from this relay. It is sent to the fuel flow controller. To find out more about these two relays, let's go to a logic diagram of the modified control system. These are the two relays that have been added to the combustion control system. There are two inputs to this relay. This input comes from a flow transmitter, and this input comes from this controller through the hand auto transfer station. The symbol on this relay means that it responds to the higher of the two input signals. It's called a high select relay. It responds by passing only the higher of the two signals through it. This higher signal is the set point for this controller. There are two inputs to this relay. This one comes from this flow transmitter, and this one comes from this controller and through the hand auto transfer station. The symbol on this relay means that it responds to the lower of the two input signals. It's called a low select relay. It passes only the lower of the two signals through it. This lower signal is the set point for this controller. Now that we've seen the arrangement and type of relays for this system, let's see how these relays react to an increase in demand for steam from the boiler. Remember, when demand increases, airflow must increase before fuel flow. Let's assume that fuel and air are being supplied to the furnace in the proper mixture and that the system's in balance. When the system's in balance, the output signals from the fuel flow transmitter, the airflow transmitter, and the master controller are balanced, and the output signals from the high and low select relays reflect this balance. When the demand for steam increases, the steam flow transmitter senses the increase and produces an output that represents the increase. This signal goes to the master controller, causing the controller to produce an increasing output. The increased output from the master controller is sensed by both the low select relay and the high select relay. The low select relay compares the signal from the master controller with the signal from the airflow transmitter. At this time, the signal from the airflow transmitter will be lower than the signal from the master controller because steam flow has increased but airflow has not. Therefore, the low select relay allows the output from the airflow transmitter to pass through it to the fuel flow controller. This output is the set point for the controller. The fuel flow controller compares the signal from the fuel flow transmitter to set point. Since airflow has not changed, set point in the fuel flow controller has not changed. The signal from the fuel flow transmitter is at set point. Therefore, the output from the fuel flow controller will not change and the fuel flow rate will not change. While fuel flow is being held constant, the high select relay also senses the increase in output from the master controller. The high select relay compares the signal from the master controller to the signal from the fuel flow transmitter. and selects the higher one to be its output. Since fuel flow has not changed, but steam flow has, the signal from the master controller is the higher of the two. The relay allows the higher signal to pass through it without being processed in any way. This higher signal becomes set point in the airflow controller. The airflow controller compares the signal from the airflow transmitter to its new set point, computes the difference, and produces a corrective output signal. This signal causes the final control element to reposition the louvers in the air duct to increase airflow into the furnace. The airflow transmitter senses the increased flow and sends a signal representing this new flow back to the low select relay. Since this signal is still lower than the signal from the steam flow transmitter, the relay sends this signal to the fuel flow controller, increasing its set point. In response to this, the fuel flow controller produces a corrective output signal that causes the fuel valve to open more, increasing fuel flow to the furnace. Both fuel flow and airflow increase until each reaches its new set point. When they do, the system is back in balance. You've seen that by adding auctioneering control to the fuel and air control system, the system responds to an increase in steam flow by increasing airflow into the furnace before it increases fuel flow. For decreases in demand, as you recall, fuel flow must decrease before airflow decreases. When demand for steam decreases, the auctioneering part of the control system will cause the system to respond in the opposite way. It will cause the fuel flow to decrease before airflow decreases. By now, you should have a basic understanding of how auctioneering control and cascade control work together to maintain the proper heat in a boiler furnace by safely regulating fuel and airflow. But as we said before, an automatic boiler control system also has to regulate water level in the drum. When we return, we'll take a look at the multi-element control system that handles this function. We've seen in our investigation of cascade and auctioneering control how combustion is regulated in a boiler furnace. But the purpose of the combustion is to heat the water in the drum and to produce steam. So up to this point, we've really only seen part of the picture. To complete our examination of a typical boiler control system, we need to learn how the system responds to a change in demand for steam in order to maintain the correct water level in the boiler drum. When water in the drum is boiled into steam to meet plant demand, a corresponding amount of feed water is needed to replace it. Therefore, to maintain proper level in the drum, water leaving the drum in the form of steam must be balanced with feed water flow into the drum. For boiler safety, it's important to keep drum level within a certain range. If the level's too low, it could cause tubes in the boiler to rupture. On the other hand, if the drum level's too high, drops of water could be carried along with the steam flowing out of the boiler, and this water could cause serious damage to other plant processes or equipment. To prevent these problems and satisfy the plant's demand for steam, steam flow out of the boiler and feed water flow into the drum must both be balanced with the drum level. A three-element feed water control system is a multi-element control system commonly used to achieve this balance. A three-element feed water control system monitors three variables. In our example, the three variables are steam flow, feed water flow, and drum level. However, other three-element control systems may use different process variables. We can see how these three variables work together by looking at an illustration of the process. This illustration represents a boiler. As we've learned, the heat produced by the combustion of air and fuel in the furnace turns the water into steam. The water, which is commonly called feed water, enters the drum through this pipe. The water is heated and turned into steam. Steam leaves the boiler drum through this pipe and goes to various plant processes on demand. Maintaining the level of water in the drum is essential to the proper operation of the boiler and also to boiler safety. So the controlled variable in this process is drum level. To maintain drum level, feed water must enter the drum at the same rate that water leaves the drum as steam. To do this, the rate of feed water flow is regulated or manipulated. So the manipulated variable in this process is feed water flow. In order to regulate feed water flow, the control system needs to measure three variables: steam flow, feed water flow, and drum level. To see how this is done, Let's add the instruments that are used in this control system. This transmitter measures the flow of steam leaving the boiler and produces a signal that represents that value. The signal is sent to this instrument, which is a ratio controller. As you learned earlier, a ratio controller computes the ratio between two signals. If the two signals do not compare at a predetermined ratio, the ratio controller produces a corrective output signal. The other input signal to the ratio controller comes from this transmitter, which measures the feedwater flow entering the boiler. The transmitter produces an output signal that represents the value of feedwater flow. The transmitter's output signal is sent to this device, called a volume chamber. A volume chamber delays pneumatic signals or dampens fluctuations in them. We can see how it does this by looking at a simplified illustration of a volume chamber. As shown in this cutaway view, this volume chamber consists of an input port that receives pneumatic signals and a valve. The valve is comprised of a restriction and a needle with a threaded shaft. The size of the restriction is determined by how far the needle is inside the restriction. The needle is positioned by turning this dial, which is attached to the other end of the threaded shaft. The volume chamber also has a pressure-tight case and an output port. To understand how the volume chamber works, we'll assume that the input air pressure and the pressure in the chamber are equal. Let's see what happens when there's a change in the input signal. If the input signal changes, there's a difference in pressure across the valve. If the change in the input signal is of long duration, then the air that bleeds through the valve will eventually cause the pressure on both sides of the valve to be equal. In this case, the volume chamber delays the change in air pressure. If the change in the input signal is a short, temporary fluctuation, then the input signal returns to the original pressure before the pressure in the volume chamber changes very much. In other words, the volume chamber dampens the fluctuation of the input signal before the output signal is affected. The output from the volume chamber is sent to the ratio controller. So the ratio controller has two input signals, one from the steam flow transmitter and one from the volume chamber. The ratio controller compares these two signals, and if they do not compare at a predetermined ratio, it produces a corrective output signal. Let's examine the function of these instruments further by referring to a logic diagram. This circle represents the steam flow transmitter. It sends a signal to the ratio controller, which is represented by this rectangle. This circle represents the feedwater flow transmitter. The signal from the transmitter is delayed by this volume chamber before it goes to the ratio controller. We can tell from this symbol that the controller has a multiplying or ratio function, and these symbols tell us that it has a proportional plus integral output. Now let's go back to the illustration of the boiler and look at the remaining instruments in this control system. This drum level transmitter produces a signal that represents the level of water in the drum. It sends this signal to the feedwater controller. The feedwater controller computes the difference between the input from the ratio controller and the input from the drum level transmitter. This difference is compared to set point, and a corrective signal is produced and sent through the hand auto transfer station and on to the final control element. The final control element positions the feedwater flow control valve to regulate the feedwater to the boiler drum. Looking again at the logic diagram, we can learn more about the instruments we just discussed. This circle represents the level transmitter. The output signal from the level transmitter goes to the feedwater controller. We can also see that this is a proportional plus integral controller. Proportional plus integral control ensures that the water level in the drum is always returned to set point regardless of the demand for steam. The output from the controller goes through the hand auto transfer station and on to the final control element. Now that we have identified all of the instruments in this three-element feedwater control system and identified their function on a logic diagram, let's see how a change in demand for steam affects the control system and how it reacts to keep the level of water in the drum at set point. When the demand for steam changes, steam flow changes. The change in steam flow is measured by the steam flow transmitter, which produces a signal that represents the new steam flow rate. This signal is sent to the ratio controller. The feedwater flow transmitter produces a signal that represents the value of feedwater flow. Up to this time, feedwater flow has not changed, so the signal from the transmitter to the ratio controller has not changed. The ratio controller computes the ratio between the signal from the steam flow transmitter and the signal from the feedwater flow transmitter. Although the signal from the feedwater flow transmitter hasn't changed yet, the signal from the steam flow transmitter has. Therefore, the ratio between steam flow and feedwater flow has changed. The ratio controller sends a corrective signal to the feedwater flow controller. This signal reflects the change in ratio. The signal indicating the change in ratio between steam flow and feedwater flow is one of the inputs to the feedwater flow controller. The other input is from the drum level transmitter, which measures the level of water in the drum. When the demand for steam changes, drum level may also change, and the transmitter produces an output signal that reflects the change. This signal is sent to the feedwater flow controller. The feedwater flow controller compares the signal from the ratio controller to the signal from the drum level transmitter. It computes any difference between these two signals and compares that difference to set point. The feedwater flow controller sends a corrective signal through the hand auto transfer station to the final control element. The final control element repositions the valve to change the flow of feedwater into the drum. At this point, the feedwater flow transmitter measures the change in the feedwater. It produces an output signal that represents the new flow rate. The change in the output signal is sent to the ratio controller through the volume chamber. The volume chamber delays the signal that represents the new feedwater flow from balancing the signal that represents steam flow. This delay gives the system time to correct the water level in the drum before the change in the feedwater transmitter signal is sent to the ratio controller. When the signal in the volume chamber has been delayed for the designated time, the signal from the feedwater transmitter is sent to the ratio controller. The ratio controller computes the ratio of the signal from the steam flow transmitter to the signal from the feedwater flow transmitter. The output signal from the ratio controller reflects the change in the feedwater flow and is sent to the feedwater controller. The feedwater controller compares the signal from the ratio controller to the signal from the drum level transmitter. As you recall, the signal from the drum level transmitter represents the changing drum level. After computing the difference between its input signals, the feedwater controller compares the difference against set point. It sends a corrective output signal through the hand auto transfer station and on to the final control element. The final control element repositions the feedwater flow control valve to regulate the feedwater to the boiler drum. This process continues until the drum level returns to set point and the steam flow out of the drum is balanced by the amount of feedwater into the drum. Looking back over the boiler control systems we've discussed, we can tie the information together with a few general points. We've seen how the heat needed to produce steam is maintained by regulating fuel and air into the furnace. And we've shown how water level in the drum is maintained by regulating feedwater into the drum. It's true that changes in the fuel or airflow may not directly affect drum level, and changes in drum level may not directly affect the fuel or airflow. However, changes in steam flow will affect all the other boiler control systems, fuel, air, and drum level.